Okay, the last part of the course, we're going to be dealing in a topic that's going to be really kind of different from what we've been talking about in terms of integration and applications of integrals. What we're going to look at in the remaining, the rest of the semester is what are known as series or infinite sums. And it will at the very end come back to the idea of finding antiderivatives and sort of complete that process at the end. And we'll see some integration along the way as well. But for the most part, it will be a little bit different. In this section 10.1, we're going to talk about sequences, which are the things that we need in order to talk about infinite sums. And so let's start with sequences. A lot of you maybe have had in your past a little brief introduction to sequences and maybe some series. So let's start with this, though, assuming you haven't had any previous background to it. So a sequence is an ordered collection of numbers defined by a function whose domain is the set of sequential integers. The values of this function or the sequence are called the terms, and we generally denote the terms with a variable and then a subscript n, right, where n is some integer. Okay, so for instance, if we start with n equal 1, then the first term of the sequence is a sub 1. It's kind of like a function: input 1, output a sub 1, input 2, output a sub 2. It's exactly what it is. It's not just kind of like a function, it is a function. But these are called the terms. N is called the index, right? So the index is 1, 2, 3, and so on. So we do informally think of a sequence as just a list of these terms in order. Okay? And it's we're going to be looking at infinite sequences. I mean, you could do a finite sequence where your index goes from 1 to 6 or something, but ours will go from 1 to infinity. There will be no end to the list. It's an infinite sequence. The term a sub n is sometimes called the general term or the nth term of the sequence, and that generally will be assigned a formula in terms of n a lot of times, or some way to determine that determine the terms in the sequence. The sequence actually doesn't have to start at n equal 1 like we start here. It can start at n equals 0, n equal 2, or any other integer. So the starting point will vary depending on our needs. But they'll all be infinite sequences. Now, let's see if we can get a graph on this. It's not too bad. If that didn't make any sense, here's an example of some sequences. And we're going to list the first 4 terms of the sequence. Unless otherwise stated, I'm always going to start with n equal 1, like I did in this sequence. Like I said, we could start at other values of n, but we're going to start with n equal 1 and continue on. So when I say the first term in the sequence, I mean a sub 1. So what is that? N is 1, and I simply, in this formula, replace n with 1. Right? Negative 1 to the first power is negative 1. 3 plus negative 1 is 2. There's the first term in our sequence. A sub 2 is 3 plus negative 1, n is 2 squared. So 3 plus negative 1 is 3 plus 1 is 4. A sub 3 is 3 plus negative 1 cubed. And that's back to 2 again, right? Since negative 1 cubed is back to negative 1. You can see we've got a sort of back and forth. If I go to a sub 4, then since negative 1 to the 4th power is back to being positive 1, we're back to 4. And so the sequence is going to alternate basically between 2 and 4. Another way of writing this sequence is this way. In curly braces, we use curly braces to denote a set, and so we do think of the sequence as a set of numbers. And so it's not, so it's very common to use the curly braces denoting a set. And so in the set I can write out, and some people will write from n equal 1 to infinity here to indicate where we start and to indicate it's an infinite sequence, but we'll just assume that here. So a sub 1 was what? 2, and then comma, what's a sub 2? 4. A sub 3 is 2. A sub 4 is 4, and so on. And that pattern is going to continue. And so a lot of times if we have that pattern established, or we obviously can't write all the terms in the sequence, so we use 3 dots, which are called ellipses, to indicate that that sequence will continue forever. So this is a common way to write out a sequence as well. All right, so let's take a look at B sequence here, B sub n. So again, real easy now. We're just plugging in and evaluating. N is 1. And I get 1 up top. 2 to the first is 2. 2 minus 1 is 1. And I get 1. B sub 2. 2 squared over 2 squared minus 1. So I get 2 squared, which is 4. 4 minus 1 is 3. I get 4/3. B sub 3. N is 3. This is 2 to the third. So 3 squared is 9. 2 cubed is 8. 8 minus 1 is 7. And then b to the fourth is 4 squared over 2 to the fourth minus 1. 4 squared is 16, and 2 to the fourth is also 16. I get 16 divided by 16 minus 1 is 15. Now, unlike the last sequence, it was kind of clear what the pattern was going to be. You know, 2, 4, 2, 4, 2, 4, 2, 4 forever. Here we got 1, 4/3, 9, 7, 16, 15. It's not quite clear what's happening here as n increases. We can certainly plug in and see, but a little more complicated looking sequence here. Now, in C sub n, you might see something interesting. I don't know how many people have seen this before, but we have a little exclamation point here. So does this mean we evaluate this as 2 divided by n? Say that real loud? No. Emphasize the n? No. That's not an exclamation point like we normally use it. This is something called a factorial. Now some of you have no doubt been introduced to that already, and let me just review a little bit about factorials. Okay, so I'm actually going to start with 0 factorial. We need that to be 1, and that might be a little confusing to some of you, but that's the case. 0 factorial is 1. And we're only going to look at factorials for whole numbers. So 1 factorial is also 1. And you're probably going, what? This doesn't make any sense. But now it will begin to make sense. 2 factorial is 2 times 1, which of course is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 12. Sorry, I can't multiply today. 6 times 4 is 24, excuse me. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 24 times 5, and so on. So, and that, does that make sense now? Factorial, so you see why we call it factorial, because we are taking and multiplying, right? These are all factors. We're multiplying 5 factorials to multiply 5 and all times all the whole numbers less than, well, positive whole numbers less than or equal to 5. Okay, so 0 factorial is kind of the one that's the outlier. We have to have that true, and that might be a little troubling, but certainly if I cover that up, this pattern certainly makes sense, I hope, to you. And so n factorial, how could I write that? Well, that's n. What's the integer less than 1 less than n? Well, we could write as n minus 1. And then what? N minus 2, and so on. And that will continue all the way until we get to 3 times 2 times 1, depending on how big n is. So there's general pattern. Just a couple of observations. One thing I'll have you observe is that 2 factorial is 2 times 1, but 1 is 1 factorial. So this is the same as 2 times 1 factorial. 3 factorial is 3 times 2 times 1, but 2 times 1 is 2 factorial, so this is 3 times 2 factorial. And so on, we see this pattern progress, right? So that's going to be a helpful feature later on. And in general, you can see that I can write this n factorial is equal to n times n minus 1 factorial. Or another way of writing it is n plus 1 factorial. Notice I'm going to take n plus 1 and then take the factorial. So I need that in parentheses. It's going to be n plus 1 times n factorial. And so factorials are a very convenient way to write out compactly products like this. Okay, so with that little brief review on factorials, we're now able to answer number 3, which is what is c sub 1? It's 2 divided by 1 factorial. And we said 1 factorial was 1, 2 divided by 1 is 1. C sub 2 is 2 divided by 2 factorial. 2 factorial is 2 times 1, which is 2. 2 divided by 2 is 1. C sub 3 is 2 divided by 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. So this is 2/6, which is the same as 1/3. And then C sub 4. 4 factorial is 4 times 3 times 2 times 1, which is 24. And I get 1/12. Okay. So again, there's the first 4 terms of the sequence. So very easily to do that, not a very difficult thing. So if we have what we call, again, the nth term of the sequence, and you can see I name sequences with different letters, A, B, or C, or whatever. But the subscript will typically use n for that index. Okay. Now, another way that's important to define sequences, very useful way sometimes, if we can, is what was known as a recursive definition. In this case, we give the first term or first few terms in the sequence, and then we give what's called a recursion, a way to find the next term in the sequence given the last last few term or terms in the sequence. So let me show you this example here. Here's a sequence, and it's given recursively. Here's the recursion. And the recursion says to find the next term in the sequence, the n plus 1 term in the sequence, I take the previous term in the sequence, a sub n, and multiply it by 3. That's what this is saying. In order to get going, then I have to have a starting point, and so notice we're given the first term. A sub 1 is 2. So what's a sub 2? Right? So using this recursion, if n is equal to 1 in this formula, 1 plus 1 is 2, I get a sub 2 is what? 3 times a sub 1. So again, the recursion is, to find a sub 2, I take 3 times the previous term. Right? A sub 1 is 2, and so I get 6. A sub 3 is going to be what? 3 times a sub 2, which is 3 times 6. So we just found that value, and we can proceed ahead. So we sort of build, we can move along by finding the next term in the sequence. This is 3 times a sub 3, which is 3 times 18, which is 54, and so on. So, now with a recursion, one thing that's not as nice as the general term is, what if I want to find the 100th term in the sequence? Ooh, well, I've got to chug all the way through the first 99 and then finally get to the 100th term, right? Whereas if we have the general term, I can plug in n equal 100 and we have the term. So the general term is a little more powerful in that sense. Okay. But sometimes sequences can only be given recursively. Here's another one where we have the nth term is dependent upon the sum, of the previous two. Do you see that? Here's n, n minus 1, n minus 2. And again, in order to get going, I need the first two terms of the sequence. So c sub 1 is 1, c sub 2 is 2. So c sub 3 is going to be c sub 2 plus c sub 1, which is 1 plus 1, which is 2. C sub 4 is c sub 3 plus c sub 2. C sub 3 we just found is 2, plus c sub 2 was 1, so I get 3. C sub 5, c sub 4 plus c sub 3 is 3 plus 2 is 5. Okay, so we've already got the first 5 terms in the sequence listed, right? We said the first 4 terms. But I want to go a little further with this. Let's look at this term, or this sequence rather, listed out as I said we could before. So the first term was 1, the second term is 1, the third term is 2, then 3, and then 5. And I can just chug along here, because remember, to get the next term, what do? I add the previous 2. So 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. And I'll stop there, but we can continue. Right. So this is the sequence. Now this particular sequence, some of you might actually remember seeing this before. This is the so-called Fibonacci sequence. And it has some interesting properties, and we could talk a lot about that, but this is a good example of how we can recursively define a sequence. Okay, another direction we would like to be able to go in then with sequences is, given the terms of the sequence, you find the nth term. You find the nth term. Okay, and so what we want to see then is basically like this. Again, I'm going to start with n equal 1 first of all. So for n equal 1, I want the output a sub 1 to be 1. For n equal 2, I want the output to be 1/2. For n equal 3, I want it to be 1/4. For n equal 4, I want it to be 1/8, and so on. See how we have that? So I want a sub 1 to be 1, a sub 2 to be 2, and so on. Okay, 1, if you think all these are fractions, so think about 1 is 1 divided by 1. So you see how I want the denominator, the numerator is always 1, but if I have 1, I want the denominator to be 1. If I have 2, I want the denominator to be 2. If I have 3, I want the denominator to be 4. Okay, does anyone see how that denominator is changing as we move along? What's happening? 1 to 2, 2 to 4, 4 to 8, 8 to 16. What's happening? It's doubling each time, right? We're multiplying by 2. 1 times 2 is 2, 2 times 2 is 4, 2 times 4 is 8, so on, right? Doubling. And how do I multiply by 2? Well, by powers or exponents on the base 2, right? So if I think about this, a sub n, I got the numerator's always 1, right? But the denominator is powers of 2, right? 2 to what power? So the question is 2 to what power? Well, when I plug in 1, I want the power to be, what, 0, right? 2 to the 0 power is 1, right? So when I plug in a sub 1, I want this to be 1 over 2 to the 0 power. A sub 2, I want it to be what? 1/2, or 1 over 2 to the first power. A sub 3, I want it to be, what, 1 over, I want 4 down here, so how do I get that? 2 to what power is 4? 2 squared. A to the 4th is what? 1 over 2 cubed, right, to get the 8. You see that pattern? So I'm just incrementing by 1 each time. But this is when n is 1, the exponent is 0. When n is 2, the exponent is 1. When n is 3, the exponent is 2. When n is 4, the exponent is 3. So what's the relationship? It's always 1 less. So if the index is n, the exponent is n minus 1. Now, nth terms are not necessarily unique because it depends on where we're starting. Here I started with n equal 1. I just want to show you, if I were to instead have started with n equals 0 to be this, and then n equal 1, 2, 3, 4, and so on, what's my nth term in that case going to be? Well, in that case, it's just going to be 1 over 2 to the n, right? So starting with n equal 0. Right? And actually, and you can see that, right? So when I plug in n is 0, I get exactly 1 over 2 to the 0, which is 1. I get that first term, and then I get 1 over 2 to the first, and so on. So the bottom line is you can actually start the sequence with at any integer and then sequentially increment that. And all that's going to do is adjust this exponent on the base 2. Okay, but very common for us to start with 1. Sometimes we start at 0. So there's the difference there. Let me look at this one again. I'm going to go back to just starting with n equal 1, 2, 3, right? These are the indexes I want to start with again here. And if we look at the top, the numerator of these fractions, they're incrementing by 1 starting at 2, right? 2, 3, 4, 5 will be the next one it looks like. The denominators, the pattern looks like what? 6, 7, 8, and so on. And by the way, we're going to assume that pattern continues. We're not going to surprise you and say, the next term is something other than 5 ninths. So we're going to assume that pattern continues in this case. So what's my a sub n going to be? Well, when it's the numerator, when I plug in 1, I get 2, which is 1 more than 2. When I plug in 2, I get 3, which is 1 more than 2. 3, plug in 4. So it's always 1 more than the index. So the top is going to be what? N plus 1, right? What about the bottom? 1 output 6, 2 output 7, 3 output 8. What are we talking about there? How much more is 6 than 1? 2 than 7, 3 than 8, 5, right? So I'm adding 5 to 1, 5 to 2, 5 to 3. So I'm adding 5 to the index, right? Now, the thing about nth terms, do you know if it's correct? Yeah, you just start plugging in, right? Plug in n equal 1 and make sure you get 2, 6. When I plug in 1, I get 2 divided by 6, 2, 6, which is 1/3. If I plug in 2, what do I get? 2 plus 1 is 3, 2 plus 5 is 7, I get 3/7, which is that term. If I plug in 3, I get 4/8. And so it is clearly going to give you what you need. So you can check. Okay. Now, some special sequences. I'm going to look at 2 special types of sequences, the arithmetic and the geometric sequences. Arithmetic sequence are sequences where successive terms are found by adding a constant d. And so we're going to find an expression for the nth term of such a sequence. So we're going to start with the first term in the sequence. I'm going to call it a sub 1. The second term, a sub 2, is going to be found by taking a sub 1 and adding d to it. It's kind of a recursion if you think about it. This is an a, sorry. A sub 3 is going to be what? A sub 2 plus d. Okay? But now notice that I can rewrite this. A sub 2 I already know is what? A sub 1 plus d. Right? Just replacing a sub 2 with a sub 1. So what does this become? A sub 1 plus d is a sub 1 plus what? 2d. A sub 4 is a sub 3 plus d. A sub 3, though, was what? A sub 1 plus 2d plus d. And what do we get? A sub 1 plus 3d. See how that's working? A sub 5, what's that going to be? Dot, dot, dot. Do you see a pattern developing here? It's going to be a sub 1 plus what? 2, 3, 4d. And so on, right? A sub 6, a sub 1 plus 5d. So we see the pattern. Can we get the nth term? A sub n is equal to a sub 1 plus something times d. And what's that something? Well, if it's 3, if the index is 3, that something is 2. If it's 4, it's 3. If it's 5, it's 4. If it's 6, it's 5. It's always 1 less again, so we've seen that before. N minus 1 times D. Now that was starting with 1, right? We started with 1 as our first. What if we started with 0, a sub 0? Then a sub 1 would be a sub 0 plus d. A sub 2 would be a sub 1 plus d, or a sub 0 plus what? 2d. A sub 3 would be a sub 0 plus 3d. And you see in that pattern, then what can we observe? In this case, a sub n is just n. Sorry, a sub 0 plus nd. So again, I can start the subscript at any point, 0, 1. I can even do it at 2. And of course, it's going to affect the general term a little bit. So that's the arithmetic sequence. Let's look at the geometric sequence. The geometric sequence is found by multiplying the previous term in the sequence by a fixed value. And usually we use the constant r for that. And so let's find the nth term there. So again, I'll start with a sub 1. A sub 2 is found by multiplying r times a sub 1. A sub 3 is found by multiplying r times a sub 2. Now a sub 2, though, is r times a sub 1. And what do we have here? What's r times r? It's r squared a sub 1. A sub 4 is going to be what? R times a sub 3, which is r times r squared a sub 1, or what? R cubed a sub 1. And we see a pattern here again, just like before. What's the pattern? What's the nth term going to be? A sub n is going to be what? Looking at the very end. If it's 2, it's r to the first power. If it's 3, it's r squared. If it's 4, it's r cubed. So what? It's always 1 less than the index, n minus 1 times a sub 1. Okay. Alternatively, I'll just show you again. We could have started with a sub 0. And then a sub 1 would be r times a sub 0. A sub 2 is going to be then what? R squared times a sub 0. A sub 3 is going to be what? R cubed times a sub 0. And again, we see the pattern here. A sub n is r to now the n times a sub 0. Okay, so what we've introduced here are sequences, and just playing around with them in terms of understanding how to list terms in the sequence, how to find the general term of a sequence, and we looked at these two special sequences, the arithmetic and geometric sequence. In the next videos, we're going to begin to look at what we're really interested in, and that is what is happening to this sequence of numbers as n here, the index, gets larger and larger and larger, or shall we say as n goes to infinity. What is this sequence approaching? What number are we getting closer and closer to as we list these out? Are we getting closer and closer to a particular number? Okay, so what we want to look at is something known as the limit of a sequence. Yes, I said limit. We are going to revisit limits, if you remember from Calculus 1, and we did limits at the beginning of this course when we did the limit definition of the definite integral. So we'll do that in the next video.